for homework 8 today. I'll make that available shortly. Second exam will be out for homework 9. We finished off momentum last time, moving into a different topic today. So center of mass is that topic. Any quick questions, administrative or logistical, before we get to it? Yeah? I did, yeah. No, I don't. That's not my normal office hours. That's like the exception rather than the rule. So I realized that they scheduled your science workshop right on top of my office hours. I fixed that for next semester. So unfortunately, it was too late once I caught that for them to fix it for this semester. So yeah, if you have problems making it to my office hours before class because you're supposed to be in the science workshop, that's a little bit, backwards. So let me know if you're prevented from coming because of that, and I'll try to work something out with Tyler. Okay, any other questions before we go? Okay, so let me try to introduce this topic like so. Up to this point in the class, whether or not you realized it or not, every single object that we've worked with has been a point particle, meaning it has no spatial extent at all. Whenever we've had objects sliding on inclines or dropping through the air, whatever, we've never once addressed its size and shape, how wide is it, how tall is it, none of that stuff. So what we've been doing so far in the class is point particle physics. Our objects have generally been point particles. We're going to now start to realize that real-world objects, they have spatial extent, right? There are more than one point on that object. There's mass distributed in certain ways. So those are extended objects. So point particle, that's what we've done so far, versus extended objects. They have size, they have shape. And so if we allow our objects to have size and shape, we should go back and check some of our old laws that we are aware of and make sure that we really know how good they are. For instance, we've learned if you have a point particle and you apply a net force in a given direction, let's say like that, we learned that it accelerates accordingly. And the law for that is F net equals ma. So what if we had an object that looked like this? So something like this eraser. If we apply a net force on this eraser, let's say like that, the whole object doesn't just move or accelerate to the right. I can show you, I guess. I'll put this eraser on the table. I'll hit it on the end, and you can see, of course, do that again, clip the notebook. So you can see that it's not like the whole thing just moves, accelerates to the right. There's one point that accelerates to the right. It's something right about here. That will accelerate like that. But the rest of the object, there's some kind of rotation involved. So really, there's only one point of the object that actually follows the law. That's the center of mass. That is the one point on the object that behaves exactly the same as if all the mass of the entire object were there. Okay? So the law really is a law for one point of the object. So the center of mass, or COM as we'll abbreviate it, what it is that point of an extended object that behaves as if all the mass were concentrated there. So the physics that we learned before, which applied to the object as a whole because there wasn't really anything to it, now we learn that that actually only applies to single point. So the center of mass of an object is basically the ambassador for point particle physics. It's that point behaves no differently if we have this mass extended in some kind of size and shape, or if we had some kind of perfect trash compactor that could take the entire mass of the object, put it into a single point. If we could take all of the mass of the object, concentrate it into this point, that point would behave no differently. Another example, of course, we can talk about, this is just an arbitrary net force of whatever kind, but one of the common forces we work with is gravity, right? So we learned that when we launch a projectile into the air, the force of gravity applies an acceleration, and generally it undergoes this arc shape. Well, let's take a look at a real object flying through the air. So if you couldn't see it on the table, you should be able to see it now. Here we go. There's only one point of that object that actually undergoes that trajectory. That's the center of mass. This is the center of mass trajectory. The rest of the object does something like that. It doesn't follow the path that we have prescribed before. So we have basically a two-part mission ahead of us. Number one, finding the center of mass of some object is an important point. We already know the behavior of that point. And then, secondly, what about the rest of the object? How do we describe that? If all our previous laws only apply to the center of mass, what about the rest of the object? Well, clearly, there's some kind of rotation involved. And so we're going to become experts at describing rotation. We dabbled a little bit on rotation earlier, homework 6. Talked about what it takes to go in a circle. But we also had a lot left on the plate there that we didn't discuss. For instance, one of the things that we purposely neglected at the time was going faster or slower as we go in a circle. So we just asked, what does it take to go in a circle? We learned there's such a force requirement called the centripetal force, but that's kind of where we left it. We'll come back and we'll get really serious about rotation. Okay, this will be on homework 8. And then when we get serious about rotation, we really get serious about rotation, there'll be some on homework 8, some on homework 9, and even a little on homework 10. So before we finish the rotation unit, we will actually reach the cutoff for the second exam. So the rotation unit will be partially after the second exam. Okay, so let's go ahead and learn about finding the center of mass. Are there any questions before I do that? Okay, so let's learn how to find that. Find the center of mass. Well, for many objects, it's extremely easy because the mass is distributed very symmetrically. An example would be, for instance, this disk, okay? So this disk, if you think of the exact middle of it, the exact center, we sometimes call that the geometric center. That means just the dimensions, whatever's in the middle, just considering the spatial dimensions. Then the mass is distributed symmetrically around that. So there would be no reason to think that the center of mass was anywhere except the geometrical center, the actual midpoint of this object. So for highly symmetric objects, we have that the center of mass is at the geometric center, which is just the midpoint or middle of the object. So right away, there's a whole bunch of symmetric objects, and we just basically put the center of mass right in the middle. If we have a sphere, center of mass is in the middle. If we have uniform sphere, we have a uniform disk. we have a uniform bar. All of these things, the center of mass is not particularly tricky to find. It's exactly where you might naively just expect it to be. And if you wanted evidence of this, let me take this disk and throw it into the air. Throw it in the air in various ways. But as we learned, if you throw something straight up in the air, it will go up, it'll come back down. So there will be the center of mass, no matter how I throw this, is required to do that. The rest of the object can rotate in all sorts of ways around that, but the center of mass is constrained to go up and down. Okay? So what we really want to focus on is if we start to have some object which the mass is not uniformly distributed, what happens? It's possible for the center of mass to not be at the geometric center. So then there are two methods. The balance method, which is handy for one-dimensional objects, and the hanging method, which is handy for two-dimensional objects. They're basically the same kind of thing, except for one is for one where the mass is basically all distributed along a line, and then the other is for when the mass is on two different axes. But they both exploit the fact that the they basically exploit the force of gravity to figure something out. And I guess I should mention to you that when you're exploiting the force of gravity for this purpose, sometimes the center of mass you will hear called the center of gravity. Okay? So center of gravity, center of mass, for you, no difference. So if I think the textbook just kind of switches back and forth between those two and doesn't tell you even why. For you, there is no difference between center of mass and center of gravity. There is a difference. There's a technical difference. You would never need to know why. Okay? It would never come up for you. So just think of them as interchangeable for you. So here's how the balance method works. If we say have like a bar or something like that, a totally uniform bar, there would be two approaches to thinking about the pull of gravity on this. One, which would be kind of counterproductive and silly, would be to think of every single atom as having its own weight. Force of gravity pulls on every single thing, right? So we could go here and say force of gravity pulls on this and pulls on this, dot, dot, dot. But that's thinking of the object in a bunch of different pieces. We want to think of the object as a whole. So if you want to think of the force of gravity as a whole, you can think of the whole object as having mass m, and then you have to pick a location. Where would be the one spot that you could pretend that the force of gravity in total is acting? Well, it's at the center of mass. Okay? So the force of gravity pulls at the center of mass. And in this case, because it's a uniform bar, there's no reason to think it's toward the left or to the right. It's right in the geometric center. Okay? So we're basically pretending that this bar is kind of, imagine taking a trash compactor, putting the entire mass of the bar there, and that's where the force of gravity, of course, would pull. So it's that one point where I can condense all of the mass of the entire object into this one point, and that one point behaves no differently. And the balance method basically works on the fact that if I have a point particle like that, I can't hold it up by putting a force over here. Okay, that's like trying to hold up this pen by putting my hand over here. Okay, it doesn't work. So, of course, if you want to support this, you don't put it here. You have to hold it where the thing actually is. Then you can hold it up. And likewise over here, this force is not going to be effective. I need to put the force at the center of mass in order to hold it up. That's when it will balance. So, in order to balance an object, you have to, to balance, you have to put the support force at the center of mass. And I should emphasize that this is a single support force. So I'm trying to balance it all with just one thing. So if you want to take a one-dimensional object and you want to balance it with a single force, keep it from falling down, you will need to put the force at the center of mass. So this is a useful property because we can now use it for asymmetric objects like this. So this is an object which has more mass on one end than the other. So I'm going to just basically use one finger as my single support force, and I'm going to try to find it. First, I'll start at the geometric center, the midpoint, halfway between the ends, and I'll try it there, and it doesn't work. And the reason why is because my finger is not at the center of mass. So I'm going to just try to find it, and right about there, it balances. So I'm safely concluding that this right here, this point, is the center of mass. Okay? This is the one point where I can pretend that the mass of this entire object is concentrated. And you can notice that it is significantly pulled toward the mass that has more end on, the end that has more mass, right? It's not at the geometric center anymore. The geometric center is here, but the center of mass is pulled toward the end where there is more mass. Okay? So that is probably the biggest takeaway of center of mass. If I have an asymmetric barbell like this, this might be the geometric center, but the center of mass is significantly pulled toward the end with more mass. So I can write the center of mass is skewed towards the larger mass end. So that's perhaps the biggest takeaway here for center of mass. Now, if you don't believe me, I could, well, I'm not going to because I already broke this once and they had to fix it. But if I threw this in the air, this is the point that would move up and down. And the other points would rotate around it. Okay? So the center of mass is constrained to obey the old physics. So you can basically take the same idea and apply it in 2 dimensions as well. So for instance, I have an object like this. This is Casper. Okay, I guess appropriate for Halloween coming up. Now I could try to balance it on one finger, okay, but that's just hard to do because it's if I don't have the right center of mass going like this, it'll tilt this way, and if I don't have it in the right place going like this, it'll tilt one of these ways. So let me just suggest an alternative method of finding it, and that method is by hanging. So what I'll do is I'll hang it once, and when it is stable, the reason why it is stable is because the center of mass ends up somewhere directly below the support. So I'm holding it directly from above. So I now have safely concluded that the center of mass is somewhere along this line. I guess it also looks like I punched a hole in this ghost's head. So the center of mass is somewhere along that line. I don't know where, but I know it's somewhere along that line because you're directly supporting it from above. So to figure it out, I just pick any other point, and then that will stabilize when the center of mass is somewhere below this support, right? I'm holding it with a single support force directly from above, so that's why it's stable. And it's somewhere along this line. And of course, there's only one point that is common to both of those lines. That's the center of mass. Okay, so that's how the hanging method works. So if I were to throw Casper in the air, which I'm not going to, that would be the point where it would go straight up and straight down. Well, there might be a rotation of the rest of it around that. Okay. So again, just to jot it down, here's how the center of the hanging method works. You have an object, some weird shape. The center of mass is somewhere here, and it'll stabilize when it's supported directly from above. So all you have to do is hang it twice from 2 different points, and then you've narrowed down the center of mass from a line to a single location. So I've neglected, oh, and I guess while I'm on the hanging method, I can show you some other kind of weird shapes. Here's one. I can have this horse thing, and I can balance it on my finger, and it kind of looks strange. But of course, there's a very lightweight plastic horse and a very much heavier metal ball here. So the center of mass is skewed much toward that metal ball, so there's nothing more remarkable about this than there is any pendulum, right? Any pendulum, the center of mass of the pendulum is below the pivot point. Or here's another one. I can balance this bird on my finger, okay, and it looks somehow like it's, should be falling down, and it isn't. But when you closely examine this, this is definitely a trick bird. It's a lightweight bird with very heavy metal weights in the wingtips. So the center of mass is somewhere between the wingtips, basically, which happens to be right below the beak. So this is just a weird looking pendulum. So the center of mass of this thing is below my finger, okay? This does bring up an interesting point too, that the center of mass of an object can actually be outside the material itself. So a classic example is a ring. If I hang that once, the center of mass is somewhere underneath here. I hang it again, it's somewhere underneath here. The center of mass of the ring is here. There's no actual physical material there. That's okay. So the center of mass does not actually have to be where there is any mass. But certainly you can agree that this is a highly symmetric object, and it makes sense that the center of mass is at its geometric center. And if you don't believe me, of course, no matter how I throw this up in the air, that's the point that goes up and down, right? I can take something like this. Let me hang it once. Let me see if I can write on this without permanently damaging it, permanently marking it. So I'll hang it once. Center of mass is somewhere underneath my fingers. So somewhere underneath here. Okay, and then I'm going to hang it again. And now the center of mass is somewhere underneath my fingers again. And what I find is that the intersection of those two things, those two lines, is not in the geometric center, right? It is significantly skewed towards this side. Why is that? Well, there's a big metal mass there that is pulling the center of mass towards it. So the center of mass of this is actually a point that is significantly skewed away from the geometric center. It's just the two-dimensional version of this, right? So there's more mass on this end. There's more mass on this end, right? So the right side, the right side. This one I can actually toss without actually breaking it. So this one, when I throw it, it looks like it wobbles. And that's, of course, because it's rotating around a point that is not the geometric center, right? Okay, hopefully that comes off. Okay, so that's the basics of just kind of conceptually speaking. And now all we're going to do is we're going to calculate to follow up on that. Okay, so the calculations are going to be basically a way of quantifying this idea. So let's take a look. So let's say I have one of those asymmetric barbells like this. I'll call this mass 1, I'll call this mass 2, and I'll put some negligible connecting rod between them, I guess, just so it's easy to think of as a single object. Not that that's important. And here's what we're going to do. If we want to find the location of something, first we have to say location respect to what. So we're going to have to put down some kind of number line here for our reference. Something like this. And as part of the input, we're going to need to, of course, first identify what is the location of each of the masses. So I'll call this x1 and x2. Both of these masses, which I'll think of as point masses, have some kind of location along this number line. And then I'm going to propose first the wrong formula and then how we can fix it. Of course, one of the things you could do is just take the average of the two positions. The problem with that is it's going to wind up with the geometric center. It's just going to end up with whatever the halfway point is. It'll give you something, but not what we seek. This gives you the x of the geocenter, or really just the midpoint. But of course, that is weighing